Hello, students. We've been discussing matrix methods for solving systems of linear equations. And I think you found that that is actually a very efficient and interesting way to solve these systems and be able to keep up with all the different types of solutions that can actually evolve. For instance, infinitely many solutions, a unique solution, no solution. The matrix methods are very, very useful. And you will find additional uses for the matrix methods as you continue in STEM. Now, today, what we would like to do is to discuss matrix algebra. That is, what we want to do now is just look at the matrix as an algebraic object and study methods of computing with matrices. Again, as you continue in your STEM education, you will find many, many uses for matrices, matrix theory, and also many of you will take courses in linear algebra where you will revisit all of this information and have a greater opportunity to understand many, many of the ramifications of working with matrices. So now let's go ahead and get started. Let me share my screen. Now, as I said before, I don't think you're going to find the matrix algebra to be overly difficult. You will have, however, more time to spend on this. And what I'm going to recommend is that you go through this material fairly slowly and allow yourself time to get accustomed to working with the matrices. You're going to find that many of the algebraic principles are very similar to the ones that you already work with in the algebra that you've been doing throughout the semester and also in the prerequisite courses. So to get started, let's just go ahead and look at some very elementary operations, but keep in context the idea that we're now working with matrices. Those are the new objects as opposed to variables that we have worked with before, x's, y's, z's, whatever, or constants. Now, for the first operation, we're going to talk about addition and subtraction. Now, what we want to do before I begin this is just talk about sizes of matrices or dimensions of matrices. For instance, when we discuss the following notation, I will say an M by R matrix has M rows and N columns. So let me actually use the correct letter here. I enjoy N, but I want to use an R here for particular reasons. So when we think of a matrix, we think of its size, M by R in this particular case, where M denotes the number of rows and R denotes the number of columns. So when you write a matrix, as you saw in the Gauss-Jordan reduction, we would always have a number of rows and a certain number of columns. So when we refer to a matrix, we definitely want to talk about its size or its dimension, that is the number of rows and the number of columns. Now, why that's important is that the very first operation here has to do with addition and subtraction, which we find to be very simple operations with algebra. Now, when we discuss the addition or subtraction of matrices, the assumption is that each of the matrices is of the same size. That is, it would not make sense to try to add matrices of different sizes because we're going to define the process of addition and subtraction as adding or subtracting corresponding entries. So what we do is we would say that if we took the matrices A and added them plus B or A minus B, subtracted them, we would want to know the IJ entry. That means what row what column. Again, I denoting the row, J denoting the column. So what that would mean is that in the A matrix, you would go to the IJ entry in matrix A, and in the B matrix, you would go to the IJ entry and either add or subtract. So I've written here add or subtract corresponding entries. So this process is very, very simple. So you can see that if you tried to add or subtract matrices of different sizes, there would be actual elements in one matrix that would not have a corresponding element in the other matrix. So again, when we think about an entry in a matrix like the 1, 2 entry in the A matrix, we would certainly want to add that entry to the 1, 2 entry in the B matrix. So again, this is a natural definition, but again, it must be applied to matrices of the same size. So we'll look at some examples of that, but this is the first standard operation that we're going to be interested in. And of course, we can think of minus b as being plus a negative, like an additive inverse. Now, for constant multiplication, that's very simple. You can multiply any matrix by a constant. And what we will do is just fix some constant number, alpha, and we will multiply each entry in the matrix by that constant. So the IJ entry of alpha A is just multiplying each entry in the matrix by alpha. Notice here when we have IJ, that is covering all possible values of I and J. For instance, here, as I would run from 1 to M and J would run from 1 to R. So you can just notate that. Notice we have a matrix here of size M by R. And if we're just applying that to this definition, we could say I has a minimum value of 1 and a maximum value of M. And then J has a minimum value of 1 and a maximum value of R. Again, we're simply keeping track of the elements in a matrix by designating its row number and its column number. As I said, when we talked about the Gauss-Jordan reduction procedure to solve systems of equations, we noted how that type of designation allows for matrices to be functions in computer algorithms. That is, we can always specify a matrix and specify exactly where each entry in the matrix resides. So again, as you continue in STEM, you may be doing some computer algorithms in your engineering classes and find many, many good uses for matrices. Now, probably one of the most interesting operations that we have with matrices, and the one that you'll probably spend the most time with just to get accustomed to, is called the matrix product. So, for instance, when we think about the product of two real numbers, we don't have an issue with that. 2 times 3, 3 times 2, it's commutative. 2 times 3 is 6, 3 times 2 is 6. No problem there. Very, very straightforward. Now, when it comes to matrix multiplication or the matrix product, we have to think a little bit more and also keep in mind the sizes of the matrices. So when is the matrix product AB defined? Well, it is defined, ladies and gentlemen, if and only if the number of columns of A equals the number of rows of B. And say in some particular case that this number happened to be N. Now, this may seem a little awkward at first. When we look at some examples, it will be much more apparent why this rule is required. But what it means is that as we define the IJ entry of the product matrix, we use this N as the upper limit of a summation. So when we think about the IJ entry of the matrix product AB, we will look at the ith row in matrix A, and the jth column in matrix B, and the index will run from 1 to n. So I can remember as an undergraduate, one of my professors said it's the finger exercise. You have one finger on matrix, on the ith row of matrix A, and another finger on the jth column of matrix B, and you just run down. That is, as you move from one entry in the row I, you move to the next entry in the column J, and you just move down. He always called this was Dr. Wright called it a finger exercise because it was very easy to think of it in those physical terms. And we'll say more about that when we look at some examples. So, but for now, if you wanted to expand this matrix, basically we have the I1 element times the 1J element here, A and B. And then in the A matrix, we have the I2 element times the 2J element in B. And we keep doing these products of elements in the matrices until we get to the end of row I and the bottom of column J. So when you think about the definition, this is really, again, why this particular rule is required. Now, when you think about defining matrix products, this is not something that just comes up, overnight. This is something that's thought about. When we think about a matrix, we're actually defining a linear transformation. We're actually defining a function. And as you take your linear algebra courses, as you continue in STEM, you will see more of the more deep qualities that you get with the matrix. There's so many wonderful things that you can do theoretically and mechanically with matrices. And the matrix product is a very good example of how you can elucidate many operations in linear algebra. Now, one thing that you might be thinking of, and this has probably already crossed your mind, the matrix multiplication or the matrix product is not commutative. For instance, even if the product is defined in the reverse direction, there is nothing to guarantee that the products would be equal. So we do not have the commutativity of matrix multiplication. Of course, the products of real numbers is commutative. That is not a problem. We do that without thinking about it. But in general, the commutativity of matrix multiplication does not hold. So that's one thing we need to think about. There will be some instances where we will have the commutativity that's going to remind you of functions and their inverses when you compose them. So that will be something that we will have that we can actually use. But for now, do keep in mind as you make your notes that the product in matrices is not commutative. Now, one thing that we want to talk about as far as things of interest would be a law that we use often in real analysis when we do our college algebra. That is the distributive law. And there's no reason to think that this would not also apply to matrix multiplication distributing over matrix addition. And so basically, if we have the matrix A multiplied on the left, and then we have the sum B plus C, we can distribute the matrix A and get AB plus AC. So of course, this makes sense where it's defined. It's an identity. What is an identity? An identity is an equation that is true for all values of the variables for which it is defined. So again, when we think about that definition, we think about the fact that we are only assuming this to be true when we know that the matrix multiplication is defined and also that the sum is defined. So that's a tacit assumption when we write this down. Of course, you can't just take indiscriminate matrices and try to add them or try to multiply them. You have to think about it. It's not something in general that you can do. When you're just thinking about real numbers, you have more flexibility. Now, one thing that you've already noticed, um, zero matrices, and I haven't mentioned this because it's really kind of simple, but when we think about a zero matrix, like a 2 by 2, we're thinking of a matrix that has all entries 0. So if we think of the 0 in matrix addition, we're just thinking of adding the 0 matrix to any matrix. And of course, that would not change the given matrix A, because we would simply be adding 0 to every entry. And we know in real numbers, we call the 0 the what? Additive identity. So that's a very simple construction. And we take it pretty much for granted. Now, when we think about multiplicative identities, we want to think about the 1 in real numbers. And it's not a surprise, because when I was teaching you about the Gauss-Jordan reduction, remember the goal was to create a matrix that has as many ones and zeros as we could actually evolve. I think I said as we could stand. I mean, you try to get as many ones as zeros as you can, because that will make the statement of the solution much more easy and much more efficient. So when we think about identity matrices in terms of matrix multiplication, they look exactly like we would expect them to look. They have in this particular case, the row reduced echelon form. So of course, the 1 by 1 matrix just looks like a 1. It's just a matrix with one entry, one row, one column. The 2 by 2 case is, again, what we thought of when we were doing the Gauss-Jordan process. And also remember this, the identity matrix, the multiplicative identity matrix, is a square matrix. And we can write the identity matrix for any size, as we have here a 2 by 2, and then of course we have the 3 by 3. And you can think of this as just being vectors. That is, the first element of the vector is 1, the remaining elements are 0. So you can think of a matrix that has 1, 0, 0, 0, 1, 0, and 0, 0, 1. Just thinking of placing vectors in for the rows, or you can think of placing the same vectors in for columns. And of course, as you continue to the 4 by 4 case, you have the corresponding vectors that have 4 elements, a 1 and 3 zeros. So as you continue to work with matrix algebra, you will gain a better familiarity with the structure of the identity matrices. The 0 matrices are very easy, very simple to work with, but it will take a little bit of time to get accustomed to the identity matrices. But at least we have seen those before when we were solving systems of linear equations. And like I said before, and this should not be a surprise, the multiplicative identity matrix commutes. That is, A times I is equal to I times A, which equals A. So we do have the commutativity for the multiplicative identity. Now, one thing that's really important that you'll have time to get plenty of practice with this week with the matrix algebra are the matrix inverses when they exist. And what I've done is described here a method by which you can determine that. I've also given you a nice formula for the 2 by 2 inverse when it exists. It's good to have useful formulas, but for 3 by 3 and 4 by 4 cases, we will use the Gauss-Jordan process. Now, at least in terms of what we've actually been talking about, excuse me, in our previous notes, when would we have the existence of the matrix inverse? Well, it will be a square matrix that is row equivalent to the identity matrix. So a 2 by 2 matrix would look like this when we apply the Gauss-Jordan method. The 3 by 3 matrix would look like this when we apply the Gauss-Jordan method. And so basically what that's saying is that we can just read off the unique solution. So when we have the existence of the matrix inverse, we can kind of append that to determining a unique solution. That is, we expect there to be some type of one-to-oneness, just like we have worked with functions previously in our work with exponentials, logarithms, algebraic. The idea is that even though the objects have changed, the types of definitions, the types of operations are still the same. Now, as I've said before, and this is important, you can think of the 2 by 2 case in this more, I guess, user-friendly form. Notice I didn't do A11, A12, A21, and A22 using the letters designating the row and column. This is a very standard form for a 2 by 2 matrix, just using our alphabetic letters. A, B, C, D in that order. And so when you need to write an inverse matrix, you can simply use this formula. Now, you may have seen this in an Algebra 2 class. When you write your matrix this way, the AD minus the BC is actually the determinant of the 2 by 2 matrix. And it's easy to write. We do AD minus BC. So just a crisscross method. Now, you can see if the AD minus BC were equal to 0, then we could not write this formula. That is, we'd have division by 0, and that's an undefined process. So when we think about, excuse me, when we think about the inverse of a 2 by 2 matrix, we can also think about the theory of determinants. And you can easily check with the 2 by 2 matrix whether or not the inverse actually exists. And so this formula is easy to use. What you notice, ladies and gentlemen, is that the A and D just switch places, and the B and the C here have an additive inverse. So this particular formula you should use, and you should also practice the Gauss-Jordan procedure with the 2 by 2 just to get extra practice. But this is always very, very useful, especially as you continue your work in STEM when you get to your Calculus 3 course and you need to invert a change of variables matrix. This can be very useful and save you lots of time. So again, this particular formula is based more on the theory of determinants. You will find as you work in STEM mathematics that determinants have a high theoretical value. They do not supply the efficiency of the Gauss-Jordan process. However, theoretically, they are indispensable. So you will see them coming up in ways that are, in many cases, will be unexpected, but they are important. Just like thinking about logarithms, we find that logarithms are very useful to our calculations, and soon you will find how useful the trigonometric functions are. Now notice, and this is very important, we also have the commutativity of the matrix and its inverse, just like we were doing composition of functions. So, and that's exactly what this is. A times A inverse equals A inverse times A, which is the identity matrix. So in these cases here, you have the commutativity of the matrix multiplication. So don't get excited that, oh, it's actually commutative. No, it's not. It's just that in these particular cases, we do get the commutativity of the matrix product. Now, one thing that we'll talk about in an exercise is a process of solving systems. Remember before, when we used the matrix, we would have the coefficients, and then we would have the basically right-hand side. And so we would just do away with the variables because we would align the coefficients for each variable in a very systematic way. So we did not have to carry the variables around. But now, if you think about what we're doing, you can think of the matrix product, that is the matrix of coefficients times the vector of unknowns equals the right-hand side matrix. So you can think of a system of equations as written as a matrix equation. Now, of course, if the inverse exists, you can actually left multiply, as we've done here, by the inverse of A, and then get an equation x equals A inverse times matrix B. Notice I've written left multiplication of B by A inverse, and that will give you the actual coordinates of the solution vector. Now, of course, this is very limited. If we do not have a unique solution, this procedure would not be applied. But when it is applied, it can be very, very useful, and you can find many models for which the coefficient matrix will be invertible, especially in linear algebra, but also in classes like economics. Those of you that take economics classes will find good uses of matrices. So let's look at some examples. Now, some of these are quite simple, and that's fine because we have to get started and build some confidence. So don't look at the simple problems as being a waste of your time. Just give yourself time to get used to the idea. You'll find certain things to be very, very simple. But the matrix multiplication and the distributive laws and the Gauss-Jordan process to compute the inverse will take a little bit more practice, but not a lot. Spend a lot of time solving systems of equations as we did in the previous lecture, and you'll feel very comfortable as you build more understanding of the matrix algebra. Now, in this particular example from your lecture notes, you just have two matrices. And notice here, these matrices have the same size. You have 2 rows and 3 columns. So this is a 2 by 3. And this is also a 2 by 3. So it would make sense to subtract them and to add them. Now notice what I did here. You can always think of subtraction as plus a negative. So you could do plus and then do the negative of B, which is basically multiplying matrix B by the constant -1. That's how we define subtraction. That is the addition of the additive inverse. So when we say addition and then subtraction, we're basically repeating ourselves, but it's important to think about delineating the operations as separate, especially when we are trying to trigger the idea of the additive inverse. So now, of course, if we do the addition first, remember, like I said before in the definition, we simply add corresponding entries. So we have 0 plus 4, which gives us 4, 1 plus 1, which gives us 2, -6 plus 0, which gives us -6, and then we have 1 plus -4, which gives us -3, 5 plus 4, which gives us 9, and 4 plus -4, which gives us 0. So addition is very, very simple. Subtraction also. Now, if you wanted to think of this alternate definition of subtraction as adding the additive inverse, we can simply multiply each of the entries in matrix B by -1 and get the following matrix: -4, -1, 0, 4, -4, and 4. And so when we actually subtract, we can just add matrix A and the additive inverse of B. So now we have 0 plus a -4 gives us a -4, 1 plus a -1 gives us a 0, -6 plus 0, -6, 1 plus 4, 5, 5 plus a -4, 1, and 4 plus 4, 8. So you will not find addition and also subtraction to be difficult at all. And remember, these operations are only defined for matrices that have the same size. So that's a very simple application. Now, from your lecture notes, I want to just talk about a very simple operation where we combine the subtraction process with constant multiplication. For instance, if you have these two matrices, excuse me, which are of the same size, again, 2 by 3. So I'll just emphasize here, same size. And that seems to be something that should be very obvious, but again, these are operations that must be defined relative to the objects with which we are working. So we do it. So now notice we have these two matrices and we want to add to the matrix 2A the additive inverse of the matrix 3B. So now what you can think of, just like we did before, you can now say 2A minus 3B would just be 2A plus negative 3 times B. That makes the process a little bit simpler. So now what we can do is just multiply all of the entries in matrix B by negative 3. So notice here, negative 3 times 4 is negative 12. Negative 3 times 1 is negative 3. Negative 3 times 0 is 0. Negative 3 times negative 5 is positive 15. Negative 3 times 2 is negative 6. And negative 3 times negative 3 is 9. Now, of course, we can do the same for 2A, just multiply each of the entries in matrix A by 2. So the 0 becomes a 0, 4 becomes an 8, negative 2 becomes negative 4, 1 in both cases becomes 2, and 3 becomes 6. So if you do this work ahead of time, it's very simple to subtract the matrices simply by adding the matrix 2A to the matrix negative 3B. And so when we add corresponding entries, we get a negative 12, 8 plus a negative 3, a 5, negative 4 plus 0, negative 4, 2 plus 15, 17, 2 plus a negative 6, negative 4, and 6 plus 9, 15. So the process is very, very simple. And of course, constant multiplication is likewise simple. Again, you can multiply any matrix by a constant. You simply multiply every entry in the matrix by that fixed number. And again, that requires every number. Each entry in the matrix must be uniformly changed when you have constant multiplication. Now, let's look at a product. Now, what I have here, again, is a very simple situation to show you how you can actually do the summation process without a lot of difficulty. Remember when I expanded the matrix, you just had the entries, corresponding entries from each matrix multiplied and then added. Remember, the summation sign means addition. So for each term that's generated, they are all added, a sum, so to speak. You will use more sums as you continue in your STEM mathematics. Again, we don't use as many sums in the college algebra, but when we get to pre-cal, we will have opportunities to use sums, especially towards the end of the course when we do induction, we do arithmetic and geometric sequences, and the binomial theorem. There will be many opportunities to utilize sums. So notice here, and this is very important, we're asked to compute the product A times C. Notice A is on the left, C is on the right. Now, what is the rule? That means in this particular case, we have to be able to do the finger exercise, so to speak. So what we see is that when we write down the size of A and we write down the size of C, we see that the number of columns of A must equal the number of rows of C. So you don't even have to even think about that so much as you simply write down the actual sizes. And then the number of columns here of the left matrix must be the number of rows of the right matrix. And that gives you a very, very simple way to check. Now, what you're going to also notice is that the numbers that get left out give you the size of the product. So the product size will just be the numbers on the extreme that were ignored, so to speak, 2 by 2. So when you think of the matrix product in terms of these parameters, that sum looks very simple now. It doesn't look nearly as abstract. So what I would recommend to get used to this is, again, just write the matrices in the order, and then we can do the finger exercise. So we're on row 1 here, column 1 here. So 0 times 3 is 0. 5 times 2 is 10. Negative 4 times 6. And excuse me, don't slip over to the next column. Negative 4 times negative 2, 8. That, when you do the finger exercise, make sure you don't wade over into the second column. That could be pretty catastrophic. So now we can see this is the 1, 1 entry. Now we're going to go to row 2 of the left matrix, and we're still on column 1. So I'll go ahead and write this down so you can see that. So we have 1 times 3, 3, 1 times 2, 2, and 3 times negative 2, negative 6. That gives us the 2, 1 entry. And notice you can write the negatives in place of the plus, again, remembering that we're just defining addition. So you can carry along the minuses. That's not a problem. And now, of course, over here, and we look at this, we're going to have row 1 of the left matrix and column 2 of the right matrix. So 0 times 1 is 0. 5 times 1 is 5. Negative 4 times 6, that's what I was trying to compute before, negative 24. And then for the last entry, which will be, in this case, row 2 of the left matrix and column 2 of the right matrix. So we have 1 times 1 is 1, 1 times 1 is 1, and 3 times 6 is 18. So if you want to just put blanks in the product matrix and then fill them up with the actual separate products from the rows and the columns, that might be a very simple way to do it, just to keep track of everything. Now, of course, when the numbers are really, really simple, it's easy to do in your head. When we're doing the Gauss-Jordan process, we don't have to keep up with as many products. We're just multiplying one row by a number and adding it to another. So that's just a very small, short calculation. We're not having to keep track of a bunch of sums. So you might find this to be a little bit simpler to write this way as you get accustomed to this. Now we just do the summation process. 10 plus 8, that gives us 18 for the 1, 1 entry. 5 plus a negative 24, that gives us negative 19 for the 1, 2 entry. And now here we have a 5 minus a 6. That gives us negative 1 for the 2, 1 entry. And here we have a 1 plus a 1 plus an 18, which gives us 20 for the 2, 2 entry. So remember, think about the finger exercise. The left matrix, you are moving along the row. In the right matrix, you are moving down the column. And that's exactly why, as we see here, the number of columns of the left matrix must equal the number of rows of the right matrix. That's always the case, and it doesn't matter how theoretically powerful you get in linear algebra, you will remind yourself of that over and over. When you actually prove that matrix multiplication is associative, it's just manipulating the definition. Again, remember, as we do work with new objects, all of the undergirding structure is based on the work that we've done previous. So we notice that once we start applying the definition of matrix multiplication, we're just back into the real numbers when we're looking at the separate entries. So again, we apply what we already know to the new definitions. So we're not starting over. We have to remember that we're working with a new object, but the proof and the work that we do is really usually 80% based on what we already know. So keep that in mind. And I don't think you'll find this to be overly challenging, but very interesting. Now, what we have in this particular case is an example from your lecture notes on the distributive law. And it has the same flavor as the last problem, but notice the difference here. We have matrix A and matrix B of the same size. So we could add or subtract those matrices. And notice in each case, this is a 2 by 3, 2 by 3. And here we have a what? A 3 by 2. So what we're asked to compute is CA plus CB. But of course, we don't want to do that. I mean, we have an identity. We have the distributive law. So basically, we could factor to the left the matrix C. Okay, that's the distributive law. So notice, and this is very important, if we have C as the left matrix, we see the number of columns here is 2, and the right matrices have number of rows 2. So we can see that that particular matrix multiplication is defined. So again, we see that the number of columns of the left matrix C is equal to the number of rows of the matrices A and B. So now, just to make the process easier, we'll just use the identity for the distributive law and add matrices A and B. So we have 0 plus 3 is 3, 1 plus 1 is 2, -1 plus 0 is -1, 1 plus -4 is -3, 2 plus 3 is 5, and 4 plus -4 is 0. Now we can simply write the matrix C on the left. That is, now we do the finger exercise, and notice this is very interesting. We know these two numbers are equal, but now the product matrix is larger. It's a 3 by 3. That is, remember, we ignore the outer numbers. Before we even look at those, we have to make sure that the inner numbers are equal. Remember, just by looking at the sizes of the matrices, you get much information before you even do any calculations. So now, if you think about this, the 3 by 3 will have 3 times 3 or 9 entries. So we'll do this just like we did before, but now we're going to have fewer summation. We'll have fewer sums. The summation's the same in the definition, but we have fewer sums. We're, in this case, just adding 2 products from the matrices. So now when we look at this, we'll just move this way. So we have row 1, column 1. So we have 12 minus 3, which we put here. Now move to the next row, stay with the first column here. We have 6 minus 18. And then -3 minus 3 right here. Now we'll move over again to the second column of the A plus B. So we have 8 plus 5 right here. Then we have 4 plus 30 right here. Third row, -2 plus 5 right here. Now again, we go back to the first row, and now we're on the last column, the third column of the right matrix. -4 plus 0 right here. -2 plus 0. We like the 0 entries right here. And negative times a negative, 1 plus 0 right here. So again, we have 9 entries, 3 by 3, and now we simply add the mini product, so to speak. So we have 12 minus 3 is 9. 6 minus 18, negative 12. Negative 3 minus 3, negative 6. 8 plus 5, 13. 4 plus 30, 34. Negative 2 plus 5, 3. Negative 4 plus 0, negative 4. And then negative 2 plus 0, negative 2. And 1 plus 0, 1. So the process is just broken down into very simple arithmetic. But the process is made more difficult because there's more arithmetic to do. We don't often think of long problems as necessarily being difficult when we look at the parts. But when you put everything together, a longer problem takes more concentration, more thought. And so we would think of that as involving a longer concentration effort, so to speak. And that really does make a problem more challenging. Shorter problems, the attention span a little less, maybe not as difficult, but everybody thinks of problems differently. Now, I wanted to show you the Gauss-Jordan method with the short 2x2 formula. Now, what I tried to do here is keep these a little neater. So I corrected some of this so you could see this a little bit more clearly. And I will note this. Remember when we did the Gauss-Jordan technique, I didn't put the vertical line between the coefficient matrix and the right-hand side. I said you can put that in or leave it out. Now, when we do the Gauss-Jordan method for the inverse, I actually do add the vertical line. Again, you don't need to. I just think in this case, it separates the given matrix from the corresponding identity matrix of the same size. And so that's why I want to use this notation and then parrot that notation here. I did not really do that with the Gauss-Jordan process when we were using that to solve systems. So I did not use the vertical line. Again, that is your choice. But here I want to because of the notation that I'm using. Now, we've got two matrices. They both have inverses. So as I said before, ladies and gentlemen, if you have a 2x2 matrix, you can use the corresponding determinant formula to compute the inverse. You can also use the Gauss-Jordan process. I'm going to highlight that on the 3x3 case. Now notice here, again, you can use the DET for determinant. That's basically just the AD minus the BC. So we have 16 minus 14, which gives us a 2. That's non-zero. So we do know that the inverse of this 2x2 matrix does indeed exist. And then the quick process, we invert the determinant to get 1/2. And then we simply interchange the A and the D to get a 2 and an 8. And then, of course, the B and the C get an additive inverse. So whatever the entries are in the original matrix, we use the formula to adjust them in the matrix of the inverse. Now, of course, if you use the Gauss-Jordan process, you could actually derive this formula very simply. So in this case, this is a 2x2 matrix multiplied by the constant 1/2. So we get a 1/2 times 2, which is 1. We get a 1/2 times a -7, which is a -7/2. We get a 1/2 times a -2, which is a -1. And we get a 1/2 times an 8, which is a 4. So we get the inverse very handily using the determinant formula. And you should use that. It's a very useful formula. You'll get plenty of practice applying the Gauss-Jordan method to the 3x3 cases and even 4x4 cases. But the 3x3 case gives you plenty of practice. And what you're going to find here, do not worry if you generate fractions. Fractions will always abound. Sometimes when you compute an inverse matrix, all the entries are fractions. There are no integers. you're probably going to end up with more fractions than you would like. But again, remember the arithmetic dictates what you get in the entries. Now, for this matrix here, note this is a 2 by 2, this is a 3 by 3. And what we want to do, and this process is steeped in what we call elementary matrices. That is, we start out with the combination matrix, so to speak. We have the matrix B appended to the corresponding 3 by 3 identity. So what we want to do, and this is the reason this actually works at all, we want to apply the Gauss-Jordan procedure here to convert the matrix B to the corresponding identity. But as we apply those elementary operations, we record them in the identity matrix. And the recording of those elementary matrices actually produces the inverse matrix, because as we multiply all of those elementary matrices together, we basically end up with a left inverse of B. Matrix inverses are unique. So once we build that, then we know that the product of those elementary matrices is indeed what we're looking for. So again, this process utilizes the theory of matrices and the uniqueness of the multiplicative inverse to provide us with a very, very useful method for computing the inverse. And what's nice about this, ladies and gentlemen, is that it's no different from solving the systems of equations which we did in the previous section. The idea is that instead of having one column here, we've added two additional ones. So there's some extra arithmetic. There are two additional operations that are required that we did not have in the previous computations, but they're the same. So first, what we're going to do, and notice here what I've written here, once we get to this point, we've arrived at the inverse matrix. And let me show you, you actually already know how to do this. Now notice, we want to convert this to the row reduced echelon form, but boy, this is a nice matrix. We already have a 1 and a 0 here, so we're good with that. We're going to keep that, and we want to, again, move down the column, create a 0, move over, create a leading 1. And the way this is set up, we can kind of get two operations done for free. Notice here, we need a 0 here. We've got our leading 1, so we're going to multiply the first row by 3 and add to row 3. So I've got the operation right here. So notice we have the 3 plus the -3 gives us a 0. And then we have -3 plus -4 gives us a -7. And then, of course, -3 plus 0 gives us a -3. Now, of course, over here, we do the same thing. 3 plus 0 is 3. 0, 0, no change. The 0 and the 1, no change. Now, notice, since this was only operating on rows 1 and 3, putting the result in row 3, so row 3 was materially changed. We do need a leading 1 in row 2, and since that's existing as it is, we're not utilizing it, we can go ahead and multiply row 2 by 1/2 to get the leading 1 here. So notice I just added this, I just kind of snuck this in because it's certainly possible to go ahead and do that. So now we get what? A 0, we get a 1, we get the 1/2, and then of course over here 0, 1/2, and 0. So now when we look at this, we've got the 1, 0, 0, and a 1. So we're well on our way to the row reduced echelon form. Now at this point, we know that below this leading 1, we need a 0. So we can multiply row 2 by 7 and add to row 3, as I've written right here. So notice we just do it. The 0, no change. Now we have a 7 plus a -7, 0. Notice here, and what's interesting about all of this that you can see when we actually work on this problem is that it gives us just such a nice way to look at these types of problems. Now notice, here we multiply by the 7, we get a 7/2, and the 3, we can just write as a -6/2. So 7 minus 6 is a 1, so we get a 1/2 here. Now let's just keep going. The 0 here doesn't change, so we multiply by 7, we still have the 3, but 7 times the 1/2 gives us a 7/2 plus 0 is the 7/2, and of course the 0 doesn't change the 1. So again, just remember, we want to create the 0 here, so we multiply row 2 by 7, and we add to row 3, and now we've got the new row 3 here. Now, when you look at this, you're thinking 1, 0, 0, 1, 0, that's good. We need a 1 here, we need a leading 1, so we can get that by just multiplying by a 2. So notice row 3, as I've notated here, we multiply by 2. So no change, 1/2 times 2 is 1. Now we multiply all of this by 2. 2 times 3 is 6. 2 times 7/2, well, that's nice. The 2's absorb. We have a 7. And then, of course, 2 times 1, 2. The products are always easy, just the constant multiples. We do have to think about multiplying row by number and adding. That's an additional operation. But notice here, we're in very good shape. And what you can see now, we're almost home. We need a 0 here and a 0 here. So to make this a 0, we can multiply row 3 by -1/2 and add to row 2. And then to make the 0 here, we can just simply add row 3 to row 1 because the 1 and the -1 are additive inverses. So now we're good to go. So now we have -1/2 times row 3. Notice no change here, so the 0 and the 1 are preserved. Now we have a -1/2 plus 1/2. We had a 0, and then a -1/2 times 6 gives us a -3. So very good. And then now we have a -1/2 in this particular case times row 3. So that gives us a -7/2 that we have here, and then we add the 1/2. So that gives us a -6/2, which gives us a -3. Now, lastly, we have the -1/2 times the 2. That gives us a -1 plus 0, -1. So just like before, we're producing the recording of the undoing of matrix B in the 3x3 matrix, which will allow us to produce the inverse matrix. Now, notice we're good here. For the last one, we want the 0 here, so we're going to add row 3 and row 1. So again, notice 0, 0, no change. The 1 and the -1, no change. 1 plus a -1, 0. Now, 6 plus 1, 7. 7 plus 0, 7. 2 plus 0, 2. Remember, the row listed second is where the result is stored. Always. That's the notation that is used, and it's the most efficient to use. Now, when we look at everything, we're thinking, well, we're almost there. We just need a 0 here, but what could be simpler? That's just like this one. For instance, we basically multiply row 2 by 1. That just says add row 2 to row 1 and place the result in row 1. So notice here, 0 plus 1, no change. 0 plus -1, 0. 0 plus 0, no change. Now, -3 plus 7, 4. -3 plus 7, 4. -1 plus 2, 1. So aside from just a few fractions with 1/2, which were not very difficult, we had a fairly simple process. Now, do not worry if you evolve fractions and you have fractions in your answer. They will come up much more often. Doesn't matter. You simply provide the elementary operations to produce the row-reduced echelon form. And by this process, we record all of those elementary operations in the corresponding identity matrix, in this case, which is 3x3. And then when we're done here, we have moved from BI to IB inverse. Remember the product of all of those elementary matrices produces the inverse matrix. And this is, again, when you take your linear algebra, you will delve more deeply into that and be probably a little bit more convinced. But just remember, as we record the process to produce the row reduced echelon form, we build the inverse. So we accomplish two tasks. Again, this tells us when it's time to stop. And you can check your work here. You can check your work as you move along. And once you produce this, you know what is here is the inverse matrix. So now what I did was record it here. So we have 4, 4, 1, -3, -3, -1, 6, 7, 2. That is our inverse matrix. And as I've written here, the product of elementary matrices. Every time we write down these operations, these are called elementary row operations. Remember, that's what we started with. But one thing that we don't use a lot is the interchange of rows. For instance, we can always interchange rows. That's not a problem. But that doesn't arise as much as these two operations. That is adding a non-zero or just adding a multiple of one row to another, or then multiplying a row by a non-zero constant. Those are going to get the most play because those will allow us to produce the leading ones, the ones, and also allow us to produce the what? The zeros. And those are what are required. So the best theoretical basis now, aside from the elementary matrices, that we know we are producing the inverse matrix is that we are showing that the given matrix is row equivalent to the corresponding identity matrix. And so that is giving us the unique solution, so to speak, the unique solution. But instead of having one right-hand side, we have three. We record the process and then develop the inverse matrix. So as you practice, and you'll have plenty of time this week to practice with the matrix algebra, and it will take a little bit of time to get used to, but you're going to see how this process ties directly into the process of solving systems of equations, because when you think about it, if we cover this up, that's exactly what we've been doing. If you cover these two columns up, that's another system of equations. And if you cover this up, that's another system of equations. So we're basically solving three systems at one time because we're adding two additional columns. So there's nothing new. It's just two additional operations that are required. Otherwise, it's the same process. Now, the last example is what I showed or promised from your lecture notes, is that in the case of an invertible coefficient matrix, you can actually apply the inverse matrix. So again, this is not something that you will use often. We know that the Gauss-Jordan process is by far the most efficient, the most mathematically elegant, because it covers everything. If we have no solution, we know it. If we have a unique solution, we know it. If we have free variables, we know we have infinitely many solutions. The Gauss-Jordan process encodes everything that we need as we work to row-reduced echelon form. We have everything we need to make a conclusion about the system. Now, for instance, in this more specific example, I just want to show you how you can actually use the inverse matrix here. Notice we have a system, two equations, two unknowns. That is, we have 9x plus 8y equals 3, and we have 3x plus 3y equals 6. Now, if we break this down and get rid of the X and the Y, at least to write matrix A, we have a coefficient matrix 9, 8, 3, 3 for A. Now, the problem actually gives us the inverse matrix of A. This is a 2 by 2 matrix. You can see we have the 27 minus 24, which is 3. That is a non-zero number. The determinant of A is non-zero. So we do have the existence of the not the additive inverse, the inverse matrix, multiplicative inverse. So now the only other ingredient we need is the right-hand side. And using the notation that I used earlier, we just call that matrix B. And notice that's just a column matrix. So what we're doing is we're using the matrices to identify the coefficients. We're using matrices to identify the unknowns and then the right-hand side. But notice this just gives us AX equals B. But since the inverse matrix exists, we know now that we can just left multiply B by the inverse of A. So the solution matrix is just A inverse times B. That's it. So now we just go ahead and juxtapose. We put the inverse matrix 1, -8/3, -1/3 on the left. And then on the right, we have the column matrix 3, 6, which is the right-hand side. So now we can just do the finger exercise, but it's a lot shorter. So we have 3 times -8/3 times 6, as we have here in the first entry. And then we have -3 plus 3 times 16. So now, of course, notice the 3 absorbs into the 6 to give us a 2. 2 times -8 is -16 plus 3 gives us a -13. And then, of course, here we have an 18 plus a -3, which gives us a 15. So now we have the so-called solution vector, but since we started with the standard system here, 2 equations, 2 unknowns, we can just write our solution as an ordered pair and just pick the actual X coordinate and the Y coordinate of the solution from the solution vector. So again, this is not a major result. We often can find certain models in economics for which coefficient matrices are invertible by design. And this can be a very useful way to do many computations if the coefficient matrix stays the same and the only thing that's changing is the right-hand side or the B matrix. So again, this is just an additional technique. We will always utilize the Gauss-Jordan process to create the reduced row or the row reduced echelon form because that gives us the most efficient way to produce a solution or a lack of it. And you know, I shouldn't even say that, you know, if the solution is no solution, that we're done. So we don't even have to specify that. So as I've said before, take the time this week to master the matrix algebra, focusing on the matrix multiplication. And I think you'll find that as you start to compare this to what you did with the Gauss-Jordan process, solving the systems of equations, everything will start to come together. Again, this particular introduction to using the Gauss-Jordan process in matrix algebra is just that. It provides you with some very useful tools that you can use in other courses, especially as you continue your STEM education. But remember, when you take linear algebra, you will continue with these types of techniques and expand into vector spaces, linear transformations, orthogonality, the theory, of determinants. There's so many eigenvalue analysis, dual spaces. There's so many elegant topics in linear algebra, and they have such a unique blend, with the real variables that you have been studying. And you will see how that ties in with the calculus in your study of differential geometry and also differential and partial differential equations. So even though we're building the foundation in the college algebra that will continue to grow as you continue with your STEM education. I hope you enjoy the matrices. Like I said before, this is a very valuable technique, and it gives you a little break from some of the tedium of some of the logarithms and exponents that we've dealt with for a while. We will continue with some systems of nonlinear equations, which will not necessarily be matrix problems, but they will apply some important techniques from the work we've been doing and be another technique that you can apply when you go through the calculus sequence. Well, that's all I have to say about this. I will see you again soon. Take care.